Hey everybody. I want to talk today about how the quantum numbers we learned last week relate to the periodic trends we're talking about this week. In particular, I wanted to talk about radius. There's a couple reasons for this. One, in watching the videos about electron configurations and periodic trends, they really just do it in a classical way, a phenomenological way. They do it relative to the Coulomb force and where the electrons are, and they just say that's where the electrons are, and they don't necessarily give the best explanation for why the electrons are there. The second is because I feel like this really connects the quantum mechanics to everything we're doing, and pretty much if we get this understanding, we can almost forget about the quantum mechanics to some degree. That's because when we're looking at electron configurations, right? We're very quickly, after you watch those videos, getting quite good at writing electron configurations like 1s2, 2s2, 2p3, oh, forgot my 2 there, or just something like 1s1, right? This would be looking at the periodic table. That would be nitrogen. This would be hydrogen. And it's very easy to lose track of what these mean, recognizing them. That's the N value, L value, number of electrons in subshell. The important thing here is that this is going to be the ground state configuration, and this gives us kind of the lowest energy situation, but we can still excite to these other states. We can talk about the ground state radius of hydrogen based off of the quantum numbers and the periodic trends, or we can look at excited states like we were doing in week 1. We were exciting hydrogen to other levels. So we could look at excited states. It turns out for the rest of this quarter, we're really going to be looking at ground states, but it's important to understand that this is ground state and it still relates to these other things. Now, when we're specifically talking about radius, it turns out that the m sub l, m sub s have no effect. Now, it's possible you could make the argument that there are times when they do matter. If you applied a magnetic field, sure, but for the most part, the things we're going to be looking at, these are going to have no effect on the radius. So we're just really going to be looking at how the N value, the principal quantum number, and the L value, the angular quantum number, and these together define a subshell. So we're going to be looking at how different subshells relate to radius. And I've got a couple simulations to kind of cement these ideas of what a probability distribution is, how the different functions that these are representing, because remember this 1s, this 2s, this 2p, those are representing functions, what those functions actually look like, and how, once we understand the relation to the periodic table, we can kind of just jump to the periodic table. So here's the first thing I want us to look at. This is a simulator where we can specify which orbital we want to look at, and then we can essentially send a photon out to find the electron. And if you didn't see it, a little red dot appeared there. Right? So whenever we're talking about where an electron is around a nucleus, we really want to think about it in terms of, well, what could we actually measure? And every time we look, we're going to find the electron. Now, the problem with quantum particles is they don't sit nicely in one spot. So we can go ahead and we can look again, and we find, oh, it's moved a little bit. But that motion, if you find it again, notice it jumps across. That motion is not a classical type of motion. So we can just go ahead and look for it hundreds of times, thousands of times. And you'll notice every time we look for it, we get a new red dot, and we get a new distance from the nucleus where we have found it. So we can go ahead and stop it. And what we've got here is this is a count at some distance from the nucleus and how often we find the electron in that spot. And that gives us a probability distribution. And this probability distribution has a particular functional form to it. It rises up and then it has this exponential decay off. And so this functional form is going to be related to the wave function. This is for a 1s orbital, and this 1s designation means that we are looking at a mathematical function that has this type of shape. I want you to pay special note of where the peak of this is, because as we go to the next one, it's going to be a little bit hard to tell. But let's go ahead and look at the 2s. So we can hop over to 2s, and we can just let that run. Here we're going to see two different colors show up as we look at this. That coloration is to just make it easier to see where the probabilities are kind of changing. And for this simulation, for the 2s orbital, you'll notice we get this really weird dark ring between the red observations and the green observations. And that is because we have a node there. We have some place where we have 0 probability. I don't know why that has a little bit there. That should be a 0. But we have no probability of being at the nucleus. There's a 0 here. And in this situation, we end up with a second 0. You'll notice also that the peak, it still has the same kind of shape. It grows up and then has an exponential decay off. And you'll notice the peak is further off to the right and it's broader. So as we go to 2s, we end up with two peaks, a small peak and then a large peak. And it turns out actually, and we'll look at this with some pictures side by side, but it turns out where this node is where the peak was for the 1s. Let's go ahead and look at 3s. Make some predictions. We see that when we went to 2s, we got 2 bumps. What's going to happen when we go to 3s? As you might have suspected, with the 3s orbital, this is the n equals 3, L equals 0 case. We end up with 3 peaks. We end up with one really tiny peak close to the nucleus. We have this second medium-sized peak, and then we've got this third largest peak. You'll notice again, it's broader and it's further out. So as the n value's gone up from 1 to 2 to 3, we've seen the radius, the probability distribution, the most likely measured radius, moves out further and further away from the nucleus. We can see that behavior a little bit better if we look at something rather than looking at this kind of number of counts. If we actually just looked at the function. If you looked at Dr. Scott's video on quantum numbers last week, you saw he actually showed you the functions. They are big mathematical functions. What we care about is what they look like relative to each other. So this is a plot. This is for the 1s orbital, and we get this nice smooth curve with some most likely radius right there. And we can look at this for the 1s, we can look at it for the 2s, we can look at it for the 3s, and we can keep going. And each time we switch up, you'll notice we get another wiggle, we get a new peak, and the radius moves further and further to the right. So this gives us the first trend that we saw in our periodic trends, which is as we increase our shell, the radius gets larger. As our n value goes up, the radius gets larger. This is not just due to electron repulsion. This would happen even if we just had one electron that we were exciting to higher and higher energy states. This was like in the Rydberg equation when we talked about sending an electron off to n equals infinity. The highest I can go here is 16. Ooh, gets a little digital. Let's increase that resolution. When we go out to these large n values, we're essentially pushing the electron away from the nucleus. independent of electron repulsion. We just see the electron move further and further away. This correlates to the periodic table and seeing as we go up in our shells, the radius gets larger, not just because of electron repulsion, but also because of the mathematical functionality of the wave functions. Let's go back to a more reasonable n value, and let's look at how this behaves with the p orbitals. Now, of course, if we have n equals 1, we can't have a p orbital. So we have to go to n equals 2, and we can look at the 3 different orientations of the p orbital, the px, the py, the pz, and you'll notice that for these, we're going to get the same types of probability distributions because the orientation doesn't really change the distribution. What you'll notice, however, is that when we go to the n equals 2, l equals 1 case, our probability distribution has changed. Instead of having 2 peaks, it's not the n value that tells us the number of peaks. Right here in this 2p case, we have the same n value, n equals 2, but our L value has changed, and we see a change in the number of peaks. So here we get only 1 peak, and that peak is in a different location than for the 2s. It's a little bit broader than the 2s, and it's a lot broader than the 1s, and it's in a different location. If we look back at the 2s, so here, we'll look at it on the other one. If we go to the 2p, you know, it's changing the orientation, we essentially get the exact same probability distribution. Actually, we get exactly the same probability distribution. I just had to let it grow in again. So we end up with the same probability distribution. This one, the peak is in the same spot. The growth is about the same. The width is about the same. The decay is about the same. When we look at this in the mathematical functions, we'll see that they actually are the same. If we go to 3p, so now we're going to n equals 3, l equals 1. Here, we're going to get 2 peaks. It turns out that the number of peaks we get is n minus l. Our n value in this case is 3. Our l value is 1. 3 minus 1 is 2. We get 2 peaks. Of course, our n value went up, so we see that our radius is further away from the nucleus, and it's also a broader distribution. You can see how this gave rise to the idea of orbits and the Bohr model of the atom where you had stable orbits, because you have this range of possible places where you're going to find the electron around the nucleus, and it looks more like a wiggly orbit, right? When you look at the planets orbiting, they pretty much orbit in these elliptical shapes. These aren't really, electrons around a nucleus aren't really orbiting, but you can see how you've got these bands of stability that give rise to the idea of an orbit, which is part of why we still call these orbitals. If instead of looking at these count views, if we go to the actual n equals 2, l equals 0, notice where that peak is. When we go to the L equals 1, oh, there was an important change there. Let's look at that again. Further away, closer in. So when we increase our L value, we actually see the radius shrink a little bit. This is really important when you're looking at transition metals and the behavior of those d orbitals, but we're not going to get into that much this quarter. It's also going to explain some of the patterns we see in ionization, and the changes in ionization energies can be related to this idea of radius and the fact that the p orbital has a smaller, slightly shifted radius than the s orbitals. If we wanted to look at the d orbitals, of course we need to go to the n equals 3. And let's go ahead and look across the s, the p, and the d here. So you notice there's the s. Switching to the p is a pretty small change. And when we switch to the D, we get a bigger shift. If you want to play with this simulator, I'll make sure I include a link in the video description because it is pretty neat and you can start looking at these comparisons. But as that L value goes up, we see the radius shift further and further in. This is a much smaller effect than switching the N value. So if I go to N equals 4, big jump out in the D orbital. If I go to N equals 3, big jump in. If I switch the L value, smaller shifts. So the N value is the major contributor to the change in radius, but the L value also contributes to the radius, and they contribute in different directions. As your N value goes up, your radius increases. As your L value goes up, your radius decreases. So here's pretty much the summary of the quantum numbers' effect on radius. The first thing we noticed was we had some number of peaks. We usually like to talk about it in terms of the number of nodes. The nodes are really fascinating if you think about it. You end up with these places where you never find the electron, yet you can still find the electron in two different spots, even though you never find it in between the two. Weird quantum stuff. But essentially, we've got a number of peaks that's going to be related to n minus L, or a number of nodes that's n minus L minus 1. Don't count the origin, even though it's a point where you hit 0. This is just looking at zeros between two peaks. The book also goes over that well. We notice that as n increases, the radius increases. And we also notice that as L increases, the radius decreases. Also, I'll say this is a bigger effect. Right? This is part of why when we change our shells in the, or subshells in the periodic table, we see these large jumps in radius. But as we go across from our N to L values, we see a small change in radius. We also have to be careful because when we start looking at atoms on the periodic table and we start comparing different atoms, we're also increasing the number of electrons and the number of protons, just to throw an extra wrench in there. And this is the point where you can really start to shift back to thinking about classical phenomena, just in terms of Coulomb force and repulsion and attraction. Adding more electrons is going to cause increased repulsion. That's the idea of shielding that's talked about in some of the videos looking at the periodic trends. And adding more protons is going to increase the attraction. That's going to be increasing the Z effective, which is talked about in some of those, the Z being the nuclear number, and how effective it attracts electrons. So it's these four ideas together, the quantum numbers, which create the shells and the subshells, and the electrons and protons, which play into the Coulomb force and attraction and repulsion. And if you're thinking closely and carefully, you can kind of see how this is almost circular logic, because the quantum numbers came from the Coulomb force, and so they kind of explain each other. Again, if you want to talk more about quantum mechanics, let me know. I could go on endlessly, but I'm going to stop there because that's enough for this class. If you understand these ideas and how these can feed into the idea of the periodic trends, that's enough. If you've got any questions, feel free to email me or come to my office hours.